At some point in 2026, 4 human beings are going to be falling toward Earth at 11 kilometers per second. That number, 11 kilometers per second, deserves a moment. In 1 second, they will travel 11 kilometers. In 1 minute, they will travel 660 kilometers. They will be moving so fast that the air in front of them cannot get out of the way. It will compress. It will heat. It will become plasma, a fourth state of matter, hotter than the surface of the sun, glowing pink and orange and white, forming a sheath around the capsule that will cut them off from every radio signal, every communication with Earth, every voice from the mission controllers who have been watching over them for 10 days. For approximately 15 minutes, they will be falling through the atmosphere in a capsule surrounded by plasma, decelerating from the speed needed to reach the moon to the speed of a parachute descent, enduring forces several times greater than the force of gravity in complete radio silence. For approximately 15 minutes, if everything goes right, the heat shield holds, the parachutes deploy, and 4 people who flew farther from Earth than any human being since 1972 land in the Pacific Ocean. For approximately 15 minutes, if anything goes wrong, if the heat shield fails, if the parachutes do not deploy, if the capsule enters the atmosphere at the wrong angle, 4 people die. Not later. Not in a hospital. Not gradually. In the atmosphere, at 11 kilometers per second, before any rescue is possible, before any signal can reach them, in the most extreme environment human beings have ever deliberately entered. This video is about those 15 minutes, not in the abstract language of mission summaries and press releases, in the specific, physical, second-by-second detail of what actually happens during the re-entry of a crewed spacecraft from a lunar mission. What the engineering is doing, what the physics is doing, what the crew is experiencing, what can go wrong, and why this specific re-entry on this specific spacecraft with this specific heat shield after what happened on its first test flight is the most consequential 15-minute period in crewed spaceflight since the astronauts of Apollo 13 held their breath, waiting to find out if their heat shield had been damaged by the explosion that crippled their spacecraft on the way to the moon. Let's start where the 15 minutes actually start. Chapter 1. The setup. 10 days that lead to 15 minutes. Everything that happens in those 15 minutes is determined by the 10 days that precede them. To understand why the re-entry is as dangerous as it is, you need to understand what the spacecraft has done to get there, what physics has done to it, and what state the crew is in when the heat shield first touches the atmosphere. The Artemis II mission is a 10-day flight to the vicinity of the moon and back. The crew? Reed Wiseman, Victor, Glover, Christina Koch, Jeremy Hansen, launches from Kennedy Space Center aboard the Orion spacecraft on top of the Space Launch System. They accelerate from 0 to 28,000 kilometers per hour in approximately 8.5 minutes, enduring peak loads of approximately 4 times the force of gravity during the solid rocket booster phase. They spend a few hours in a parking orbit checking systems. They fire the translunar injection burn, which takes them from orbital velocity to escape velocity in approximately 5 minutes and 40 seconds. And then the interim cryogenic propulsion stage separates, and the crew is on their own. For 3 days, they coast to the moon. The moon grows from a bright point of light to a world filling the windows. They swing around it at an altitude of approximately 8,900 kilometers, the closest any human will have come to the moon since the last Apollo astronaut left in 1972. On the far side, for approximately 25 minutes, they are out of radio contact with Earth in the most profound silence any human being has experienced. Then they emerge from behind the moon, the signal is reacquired, and the long coast home begins. For 3 more days, they fall back toward Earth. The Earth grows from a bright blue marble to a world filling the windows. They sleep, they exercise, they conduct experiments, they monitor the spacecraft's systems, they speak with their families and mission controllers. The spacecraft is working. The journey is going as planned. And then, at the end of the 6th day of the return transit, they do the thing that determines everything else. They prepare for re-entry. The re-entry preparation begins well before re-entry itself. The crew changes into their launch and re-entry suits, the pressure suits that would protect them from rapid decompression in the event of a cabin pressure failure during the high-risk phases of the mission. The suits are full pressure capable. In the event of a catastrophic loss of capsule pressure, the suit can maintain the pressure necessary to keep the occupant alive. They are not comfortable. They are not designed to be comfortable. They are designed to keep the person inside them alive under conditions that are not meant to sustain human life. The crew straps into their seats. The seats are designed with shock absorbers that reduce the peak loads on the crew during the splashdown impact. Even with parachutes deployed, the water impact generates a force that the seat system must absorb. Each crew member is secured with a full restraint harness. They are not going to move during re-entry, regardless of what the loads are. The capsule is reconfigured for re-entry. The jettisoning of the service module, the European service module that has provided propulsion, power, and life support since launch, is one of the last major events before atmospheric entry. The service module has been the heart of the Orion spacecraft's ability to operate in space. Once it separates, the crew module is on its own, relying on its internal batteries for power, its RCS thrusters for attitude control, and its heat shield for thermal protection. The service module separation is irreversible. Once the module is gone, there is no reconnecting with it. The crew module, now alone, heat shield forward, configured for entry, is approximately 3.3 meters tall and 5 meters in diameter. It weighs approximately 9,300 kilograms, fully loaded with crew and re-entry provisions. It is moving at approximately 11 kilometers per second relative to the Earth's upper atmosphere, and it is about to hit that atmosphere. The 15 minutes begin here. Chapter 2, Entry Interface, the moment the atmosphere pushes back. Entry interface is the term engineers use for the moment. A spacecraft first encounters the atmosphere at a density sufficient to create aerodynamic forces. For the Orion spacecraft returning from a lunar mission, entry interface is defined at an altitude of approximately 122 kilometers above the Earth's surface. At 122 kilometers altitude, the atmosphere is extraordinarily thin. At sea level, the air pressure is approximately 101,000 pascals, about 14.7 pounds per square inch, the standard reference condition. At 122 kilometers altitude, the air pressure is on the order of 0.01 pascals, roughly 10 million times less dense than sea-level air. A human being at this altitude without a pressure suit would be exposed to effectively vacuum conditions. The pressure is so low that it is not breathable, not survivable, not even adequate to prevent the blood from beginning to boil. And yet, at 11 kilometers per second, this extraordinarily thin air is enough to create very significant aerodynamic forces. The dynamic pressure, the force that the flowing air exerts on an object moving through it, is proportional to the density of the air and the square of the velocity. The velocity at entry interface is enormous. Even though the density is tiny, the velocity squared term is so large that the dynamic pressure is significant. The crew does not feel anything dramatic at entry interface. The deceleration is still very gentle at this point, a fraction of a g. But the chemistry happening outside the spacecraft is extraordinary. The air at 122 kilometers altitude is composed primarily of nitrogen and oxygen, in roughly the same proportions as sea-level air. But at this altitude, the molecules are sparsely distributed. The mean free path, the average distance a molecule travels before colliding with another molecule, is much longer than at sea level. When the shock wave ahead of the spacecraft compresses these sparse molecules, they don't simply pile up the way they would in a denser medium. They collide with each other with enormous kinetic energy, and these high-energy collisions break molecular bonds. Diatomic nitrogen molecules, two nitrogen atoms bonded together, the primary constituent of air, begin to dissociate at temperatures above approximately 6,000 Kelvin. The compressed air ahead of the Orion heat shield reaches these temperatures at peak heating. The nitrogen molecules split into individual nitrogen atoms. The oxygen molecules also dissociate, and at even higher temperatures, above approximately 9,000 Kelvin, the atoms themselves begin to ionize, losing electrons and becoming positively charged ions. The result is a plasma, a soup of positive ions and free electrons that is an entirely different physical and chemical environment from the ordinary air that existed before the shock wave hit it. This plasma is electrically conductive. The free electrons allow current to flow through the plasma. This is why the plasma blocks radio signals. Electromagnetic waves are absorbed and reflected by electrically conductive media, and the dense plasma sheath around the Orion capsule is optically thick to radio frequencies. The physics of the blackout is not a signal loss due to distance or power. It is absorption by a conductive plasma that surrounds the capsule completely. The plasma also reacts chemically with the avcoat surface. The high-temperature dissociated air contains atomic oxygen, which is enormously chemically reactive, far more reactive than the diatomic oxygen in ordinary air. The atomic oxygen attacks the pyrolysis gases that emerge from the charring avcoat surface, creating a complex chemical environment at the boundary between the plasma and the heat shield. The behavior of the avcoat material in this complex chemical environment is part of what the computational fluid dynamics models attempt to capture, and part of what the arc jet tests attempt to replicate. The crew does not feel anything dramatic at entry interface. The deceleration is still very gentle at this point, a fraction of a g. But the heat shield is beginning to interact with the air molecules, which cannot move out of the way of the oncoming spacecraft quickly enough, are being compressed ahead of the heat shield in a shock wave. The compression is converting the kinetic energy of the spacecraft, the energy associated with its 11 kilometers per second velocity, into heat in the compressed air. At entry interface, the heating is modest. The plasma is not yet forming. The color of the glow around the spacecraft is not yet visible. But the process has begun. The atmosphere is touching the heat shield. The heat shield is touching the atmosphere. And from this moment, for the next 15 minutes, the aerothermal physics that was designed into the Orion spacecraft and tested in the Arc jet facilities at NASA Ames and modeled in the computational fluid dynamics codes of the engineering teams. All of it is being put to the test in the one environment that ultimately matters. Not the laboratory, not the computer, the real atmosphere, at the real velocity, with the real AVCoat material on the real spacecraft. This is the moment when the question of what happened to the heat shield on Artemis one becomes immediately relevant. The heat shield that behaved unexpectedly, that charred in ways the models did not predict, that ejected pieces of char that were not supposed to eject. That heat shield is the one currently meeting the atmosphere. The crew cannot see it, they cannot inspect it, they cannot do anything about it. It is bolted to the bottom of their capsule, and it is beginning to heat up. Chapter 3: The First Dip. Where the heating begins. What makes the Artemis II reentry unlike any Apollo reentry, and unlike any shuttle reentry, and unlike any crewed reentry from low Earth orbit that has ever been conducted, is the skip maneuver. The Orion spacecraft does not fall straight into the atmosphere on a single ballistic trajectory. It enters the atmosphere at a relatively shallow angle, generates aerodynamic lift, and uses that lift to pull the spacecraft's nose up, causing it to bounce or skip back out of the denser lower atmosphere and into the thinner upper atmosphere before making its final plunge. The physics of this is essentially the same as skipping a flat stone across the surface of water. The stone hits the water at a shallow angle. The water's surface pushes back on the stone with a force that has a vertical component, the hydrodynamic lift. If the stone is spinning, as thrown stones are, and the angle is correct, this vertical component is larger than the stone's weight, and the stone bounces back up off the surface. It then continues on its trajectory, losing some velocity with each bounce, until it finally loses enough energy that it sinks. The Orion spacecraft is not spinning like a stone, but the principle of aerodynamic lift is analogous. The capsule is oriented at a specific angle of attack, the angle between the capsule's axis and the direction of motion, that generates aerodynamic lift. The lift force is perpendicular to the direction of motion and, in the right orientation, has a component that pushes the spacecraft back up out of the denser atmosphere. The first dip into the atmosphere is the phase during which the most dramatic aerothermal heating occurs. As the spacecraft descends into increasingly dense air at still high velocity, the compression of the air intensifies, the heating of the compressed air intensifies, and the heat load on the heat shield increases dramatically. The stagnation point, the direct forward face of the heat shield, where the compression is greatest, reaches temperatures approaching 2,760 degrees Celsius during the peak heating of the first dip. The crew experiences the first dip as increasing G-load. The deceleration is building as the atmosphere increasingly pushes back against the spacecraft's forward motion. At peak deceleration, during the first atmospheric dip, the crew experiences approximately 3 to 4 times the force of gravity pressing them back into their seats. The G-forces are sustained, not the brief spike of a roller coaster, but a prolonged, pressing, inescapable force that makes every movement difficult and breathing somewhat labored. People who have experienced 4G in centrifuges describe it as feeling like someone is sitting on your chest. Outside the spacecraft, something remarkable is happening. The plasma is forming. The compression of the air ahead of the heat shield has heated the air so intensely that the electrons are being stripped from the air molecules, oxygen, nitrogen, ionizing the gas and creating a sheath of plasma around the capsule. This plasma radiates energy. It glows. If the crew could see it from outside, and some of the more rearward windows may provide a glimpse, the spacecraft would appear to be wrapped in a glowing cocoon of orange and pink and white light, trailing behind it as it streaks through the upper atmosphere. The radio blackout begins during the first dip. The plasma sheath surrounds the spacecraft completely, and plasma at these densities and temperatures is an excellent absorber of radio frequency radiation. The electromagnetic waves that carry the voice communications between the spacecraft and mission control, which travel at the speed of light, cannot penetrate the plasma sheath. The crew cannot receive transmissions from mission control. Mission control cannot receive transmissions from the spacecraft. Communications cease entirely. From the mission controller's perspective, this is one of the most intense periods of any mission. They have been monitoring the spacecraft's telemetry continuously for 10 days. They have seen every temperature, every pressure, every current draw, every propellant quantity in real time. And now, during the most dangerous phase of the entire mission, they lose contact. The spacecraft is there. It shows up on radar. They can track its trajectory, but they cannot hear it, and it cannot hear them. They can only watch the radar return and wait for the plasma to thin as the spacecraft decelerates and the re-entry heating subsides. The crew, in the radio blackout, is more isolated than any point in the mission, more isolated even than the far side of the moon, which at least had the continuity of the mission timeline and the certainty of eventual signal reacquisition. In the re-entry blackout, the crew is in the most extreme physical environment of the mission, in a vehicle being subjected to forces and temperatures at the design limit of its engineering, completely out of contact with the ground, and dependent entirely on whether the hardware performs as designed. The first atmospheric dip lasts approximately 3 to 4 minutes. In those 3 to 4 minutes, the heat shield experiences the majority of the total thermal energy load of the entire re-entry. The AV coat is charring, the char layer is building. The thermal protection system is doing its job, absorbing, in the burning of its own material, the energy that would otherwise heat the capsule's structure to lethal temperatures. And then, if the design works as intended, the aerodynamic lift takes over. The capsule's trajectory curves back upward. The atmospheric density decreases. The heating rate drops. The plasma begins to thin. The blackout begins to ease. The spacecraft is completing its skip. Chapter 4, The Skip. Where the heat shield has already failed, Once the skip phase is the period between the first atmospheric dip and the final re-entry plunge. During the skip, the spacecraft has bounced out of the denser lower atmosphere and is coasting through the thinner upper atmosphere, losing velocity more slowly than during the dip, with the heat shield cooling somewhat as the aerothermal heating drops. This is the phase that nobody fully understood before Artemis I. The cooling of the heat shield during the skip phase is not simple. The char layer that formed during the first dip, the burned, carbonized outer layer of avcoat that serves as the thermal insulator for the underlying fresh material, is hot, very hot. The outer surface of the char reached temperatures of over 1,000 degrees Celsius during the peak heating of the first dip. During the skip, the aerothermal heating drops, but the char layer does not instantly cool to match. It radiates heat to space. It conducts heat down into the underlying fresh avcoat. It gradually cools. But gradually is the key word. The char layer is cooling while it is structurally connected to the underlying avcoat, which is also changing temperature, but at a different rate, because it has different thermal mass and different thermal conductivity. The differential thermal contraction, the difference in how much the hot char layer contracts as it cools compared to how much the slightly less hot underlying material contracts, creates mechanical stress in the char layer. Specifically, it creates a shear stress at the boundary between the char and the underlying avcoat that tends to delaminate the char from the material it is bonded to. If this shear stress exceeds the mechanical strength of the char, if the char is brittle enough or the stress is large enough, the char cracks. And if the cracks reach through the char layer to the interface with the fresh avcoat, pieces of char can delaminate and be pushed off by the aerodynamic forces acting on the heat shield surface. On Artemis I, this is exactly what happened. The engineers did not know it was happening in real time during the mission. The heat shield does not have sensors that can detect char cracking or measure the thickness of the remaining char layer in flight. The only way to know was to recover the spacecraft and inspect the heat shield after the fact. Which is what happened. And what they found was that in specific regions of the heat shield, regions that corresponded to the areas of highest heating during the first dip, the char had cracked and ejected in pieces. What this means for Artemis II is this. The skip phase, which on Artemis I produced the anomalous char behavior, is going to happen again. The crew is going to coast through it. The heat shield is going to cool during it. The thermal stress in the char layer is going to develop during it. And whether the improved material in the Artemis II heat shield, the avcoat with reduced void content, manufactured to a higher standard of uniformity, is resistant enough to the thermal stress to prevent the cracking and ejection that occurred on Artemis. One is a question that has been studied intensively for 2 years, tested in arc jet facilities, and modeled in updated computational codes. It has not been tested in the actual flight environment, with actual re-entry conditions, at actual scale. The skip lasts approximately 6 to 8 minutes. During these 6 to 8 minutes, the crew is experiencing lower G-forces than during the first dip. The deceleration has eased somewhat. The radio blackout may partially lift during the skip as the plasma thins when the aerothermal heating drops. Mission controllers may receive partial telemetry, enough to know that the spacecraft is still there and still on a reasonable trajectory. But full voice communication may not be restored. From the crew's perspective, the skip phase is a period of relative, emphasis on relative, calm. The worst of the first dip is behind them. The worst of the final re-entry is ahead of them. The G-forces are lower. The glow through the windows has subsided. The capsule is flying through the upper atmosphere. They do not know and cannot know in real time what the heat shield beneath them is doing, whether it is cracking, whether pieces of char are detaching, whether the thermal protection that they need for the final re-entry plunge is being compromised by the same mechanism that compromised it on Artemis I. This is the most uncomfortable sentence in the engineering of Artemis II. Chapter 5, The Final Plunge, 11 Seconds That Change. Everything. At the end of the skip, the spacecraft's trajectory curves back downward into the atmosphere. The atmospheric density increases again. The aerothermal heating increases again. The heat shield, which cooled somewhat during the skip, heats up again. This is the second heating pulse. In the models, the second heating pulse is predicted to be less intense than the first. The spacecraft has lost significant velocity during the first dip and the skip. It has decelerated from approximately 11 kilometers per second at entry interface to perhaps 7 to 8 kilometers per second by the end of the skip. Less velocity means less kinetic energy, means less compression, means less heating. The second heating pulse is the last insult the atmosphere delivers, and it is predicted to be manageable. The question is whether the heat shield, after the first heating pulse and the skip, is still in a state where it can manage the second heating pulse. If the char ejection that occurred on Artemis I recurs on Artemis II, if the thermal stress of the skip phase causes cracks and char ejection in the Artemis II heat shield, then the fresh avcoat underneath the ejected char is exposed to the second heating pulse earlier and at a higher heat load than the models predict. The exposed avcoat will char again, forming a new protective layer, but the process is less efficient than the smooth, progressive ablation the models are designed for. The new char forms rapidly under high heat load, and rapidly formed char is less mechanically stable than progressively formed char, making it more susceptible to further cracking under the second heating pulse's aerothermal forces. This is the cascade scenario. Char ejection during the skip phase exposes fresh avcoat. The exposed avcoat chars rapidly under the second heating pulse. The rapidly formed char is mechanically compromised. Further cracking and ejection occur during the second heating pulse. This exposes more fresh avcoat, which chars rapidly, which cracks further. Each cycle of cracking and exposure depletes the heat shield thickness faster than the smooth ablation models predict. The heat shield has a finite thickness. If the cascade proceeds far enough, if the depletion rate is high enough, and the second heating pulse lasts long enough, the heat shield can be ablated through entirely. The plasma can reach the underlying structure. The spacecraft can fail. The physics of this cascade is understood at the level of its constituent mechanisms. Each individual step, char formation, thermal stress, cracking, ejection, rapid recharring, is physically explicable. What is not known with confidence is how the cascade behaves under the actual Artemis II conditions. The specific heat shield material with its improved properties, the specific re-entry trajectory with its modified heating profile, the specific realization of atmospheric density and entry conditions on the day the mission returns. The second heating pulse lasts approximately 3 to 4 minutes. During this time, the G-forces build again to approximately 3 to 4 G, sustaining as the atmosphere decelerates the capsule. The plasma forms again. The radio blackout resumes or deepens. And then something else happens. Something that has to happen. Something that, if it doesn't happen, guarantees the deaths of the crew regardless of what the heat shield does. The parachutes have to open. Chapter 6. The parachutes, the last line that has to hold. The parachute system on the Orion spacecraft is among the most complex and most carefully designed elements of the entire vehicle. It is also, in the hierarchy of systems on which the crew's survival depends, the second most critical after the heat shield. Because a perfect heat shield performance, followed by a parachute failure, is still a crew loss. The parachute system consists of 2 types of parachutes deployed in sequence. The first are the drogue parachutes, 2 of them, each 7.3 meters in diameter, deployed at approximately 8 kilometers altitude while the spacecraft is still moving at supersonic speeds. The drogues don't slow the spacecraft dramatically. Their job is to stabilize it. A capsule descending through the lower atmosphere at high speed is aerodynamically unstable in the tumbling sense. If it is not carefully controlled, it will begin to oscillate and spin in ways that make a stable parachute deployment impossible. The drogues grab the airflow and stabilize the capsule, orienting it consistently and preventing the tumbling and oscillation that would make the main chutes tear apart on deployment. After the drogues have done their work, after the capsule has been stabilized and slowed to approximately 230 kilometers per hour, the drogues are cut away and 3 pilot chutes are deployed. The pilot chutes are small. Their purpose is not braking, but extraction. They pull out the 3 main parachutes, each 35 meters in diameter, packed into 3 separate canisters. The deployment of 3 parachutes, each 35 meters across, is one of the most mechanically violent events in the entire mission. Each parachute, as it opens, generates an enormous opening load, a sudden, violent jerk as the parachute fabric catches the air and decelerates from the deployment velocity. The 35-meter main parachutes are among the largest parachutes ever built for any application. Their diameter, when fully deployed, is approximately the height of a 12-story building. 3 of them, together, provide the braking force needed to slow the 9,300-kilogram Orion capsule from approximately 230 kilometers per hour at drogue separation to approximately 28 kilometers per hour at splashdown, a safe speed for water impact. The parachute system has been tested extensively. NASA has conducted a comprehensive program of drop tests from high-altitude aircraft, testing different deployment scenarios, including off-nominal conditions, 1 parachute failing, deployment at higher than nominal speeds, deployment at off-nominal attitudes. The Orion parachute system has been tested in scenarios where it is deliberately degraded. One of 3 main chutes intentionally failed, and it has been demonstrated to safely land the capsule on 2 chutes rather than 3. The testing program is exhaustive and reassuring. It represents a very high level of confidence in the parachute system's ability to perform. But it is testing. not flight. And there are aspects of the actual re-entry environment that the drop tests cannot fully replicate. The specific temperature of the parachute hardware after re-entry heating, the specific state of the deployment mechanisms after the aerothermal and G-load environment of the entry phase, the specific tumbling or oscillation state of the capsule as it enters the drogue deployment phase. The parachutes are packed and sealed before launch. For 10 days, they have been in the parachute canisters on the crew module, experiencing the vacuum of space, the temperature extremes of being in the sun and then in shadow, the vibration of the SLS launch and the translunar injection burn. For the duration of the re-entry, they have been exposed to the aerothermal and G-load environment of the entry phase. They deploy, if they deploy correctly, at the moment when they are most needed and least recently verified. 10 days and 1 re-entry after they were last in a condition that could be tested. The deployment sequence is automated. It is triggered by signals from the onboard computers based on altitude, velocity, and dynamic pressure readings from the spacecraft's navigation and sensor systems. The crew does not manually deploy the parachutes. There is a manual override available in the event that the automatic system fails, but the nominal deployment is computer commanded. The crew in their seats will feel the drogue deployment as a sudden, moderate jerk, followed by a significant increase in the noise level. The air rushing past the parachute fabric is loud even through the capsule walls. The drogue stabilization phase, which lasts a few minutes, will be accompanied by a rocking, pendulum-like motion as the capsule hangs from the 2 drogue parachutes and swings in the airflow. Then the main chute deployment. 3 more sudden jerks, each more significant than the drogue opening, as each of the 3 main parachutes catches the air. The main chutes, once fully deployed, reduce the descent rate to the splashdown velocity of approximately 28 kilometers per hour, and the capsule hangs from them, slowly descending, the crew looking out the windows at the Pacific Ocean approaching below them. If the parachutes work exactly as designed, this is the moment when the crew knows they are going to survive. Not certain. Splashdown and water impact carry their own risks. But survival is no longer primarily a question of whether the hardware works. The worst of the physics has passed. The parachutes are supposed to take approximately 15 minutes from drogue deployment to splashdown, though the exact timing depends on atmospheric conditions. If the re-entry has proceeded nominally, the total time from entry interface to splashdown is approximately 15 minutes. If the parachutes do not deploy, if the automatic sequence fails and the manual backup fails, there is no further option. The capsule impacts the water at approximately 230 kilometers per hour, the speed at which the drogues were cut away. A 9,300 kilogram capsule impacting water at 230 kilometers per hour does not land. It hits. The impact is not survivable. Chapter 7. The specific numbers: how fast, how hot, how hard. The 15 minutes of Orion's re-entry can be described in numbers that, when stated plainly, convey the scale of the engineering challenge more clearly than any general description. Velocity at entry interface, 11.0 kilometers per second, which is 39,600 kilometers per hour, which is 32 times the speed of sound at sea level, which is fast enough to travel from New York to London in just under 6 minutes. Temperature at the stagnation point, the direct forward face of the heat shield, where compression is greatest. Approximately 2,760 degrees Celsius. The surface of the Sun is approximately 5,500 degrees Celsius. The Arc jet facilities at NASA Ames, which are the most powerful aerothermal testing facilities in the world, can produce test conditions up to approximately 5,000 degrees Celsius on small test coupons. The stagnation point temperature on Orion's heat shield during re-entry is approximately half the Sun's surface temperature. The temperature of the char on the Avcoat surface during peak heating, over 1,000 degrees Celsius. The temperature of the fresh Avcoat underneath the char layer during peak heating, approximately 200 to 300 degrees Celsius. The temperature of the crew module's aluminum primary structure during re-entry should remain below approximately 175 degrees Celsius with the heat shield functioning correctly. If the heat shield fails and the plasma reaches the structure, 2,760 degrees Celsius versus an aluminum melting point of 660 degrees Celsius. The structure burns. Total kinetic energy of the Orion capsule at entry interface, approximately 580 gigajoules. That is 580 billion joules of energy that must be dissipated during re-entry, almost entirely through the aerothermal heating and subsequent radiation from the plasma, not through the heat shield itself, which absorbs only a fraction of the total. The heat shield absorbs approximately 2 to 3% of the total heating, enough to protect the capsule's structure, but the vast majority of the kinetic energy is deposited in the atmosphere and radiated away. The plasma behind the spacecraft, glowing from the deposited energy, is visible from the ground on a clear night as a bright streak across the sky. G-forces experienced by the crew during re-entry peak approximately 4G, sustained for several minutes. For context, pilots trained for high-G environments can sustain approximately 9G with a G-suit before losing consciousness. 4G is well within human tolerance for a healthy person in good physical condition. But the crew of Artemis II has been in microgravity for 10 days. In microgravity, the cardiovascular system adapts to the absence of hydrostatic pressure gradients, the pressure differences that occur in a gravitational field between the head and the feet. The heart does not need to pump as hard to maintain circulation. Over 10 days, the cardiovascular system becomes partially deconditioned for the demands of gravity. When the crew re-enters at 4G, their cardiovascular systems, partially deconditioned by 10 days of weightlessness, are suddenly asked to perform under conditions 4 times more demanding than normal gravity. The primary concern is orthostatic intolerance, the difficulty of maintaining adequate blood pressure in the brain when G-forces are pressing blood toward the lower body. This is why pilots wear G-suits, garments that squeeze the lower body to prevent blood pooling. The Artemis II crew's pressure suits provide some anti-G protection through their design, but the cardiovascular deconditioning from 10 days of weightlessness is a real physiological challenge that overlays the re-entry demands. The crew will also be wearing pressure suits that have been worn for the entirety of the launch, transit to the moon, lunar flyby, and return transit. A suit worn continuously for the most critical phases of a 10-day mission. The suit is equipped with temperature regulation, but thermal comfort is not the primary specification. The primary specification is survivability in a cabin pressure failure, and that specification does not optimize for crew comfort over a 10-day mission. Duration of the radio blackout during re-entry: approximately 10 to 15 minutes, spanning the first atmospheric dip, the skip, and the final re-entry plunge. During this period, mission controllers have no voice contact with the crew and limited telemetry. The blackout ends when the plasma has thinned enough. As the spacecraft decelerates and the aerothermal heating drops, for radio signals to penetrate. The first restoration of communication after the blackout is one of the most significant moments of the mission for the controllers on the ground, because it is the first confirmation that the capsule is intact and the crew is alive. Splashdown velocity: approximately 28 kilometers per hour with all 3 main chutes deployed. The energy of the water impact at this speed is absorbed partly by the parachutes, which are still attached at impact and provide some continued drag, partly by the water itself. The surface tension and viscosity of the ocean provides a cushion, and partly by the seat shock absorbers in the capsule, which are designed to reduce the peak deceleration experienced by the crew to approximately 15 to 20 G over a very brief duration, fractions of a second. The brief high G spike at splashdown is intense but brief enough that it is within human physiological tolerance. In the 15 minutes from entry interface to splashdown, the Orion capsule slows from 11 kilometers per second to approximately 8 meters per second, from 39,600 kilometers per hour to about 28 kilometers per hour, a velocity reduction of more than 99.9%. Every bit of that velocity reduction is accomplished by the atmosphere alone, by aerodynamic drag from the heat shield and the capsule's blunt body shape, and by aerodynamic drag from the parachutes. There is no propulsive capability available during re-entry. There are no engines the crew can fire to slow down faster, no alternate trajectories they can fly to reduce the heating, no way to extend the re-entry if things go wrong. The physics takes over, and the only question is whether the engineering matches what the physics demands. Chapter 8: What the crew is experiencing. The inside of those 15 minutes. The numbers describe the physics. What they don't fully capture is what it is like to be inside the capsule during those 15 minutes. The crew has been in the spacecraft for 10 days. They have adapted to the microgravity environment, the floating, the reorientation of their vestibular systems, the fluid redistribution from their lower bodies to their heads that gives all long-duration spaceflight crew members a faintly puffy face and stuffy head sensation. They have built a rhythm of daily life inside the capsule that, in its ordinariness, has made the extraordinary environment somewhat familiar. They have slept, eaten, exercised, talked to their families, done their work, and settled into the specific texture of life in a machine that is far from Earth. Now they are strapped into their seats. The familiar environment of the floating capsule interior is gone. The microgravity that they have been living in for 10 days is about to be replaced decisively by several times the force of Earth's gravity. The weight of their own bodies, which they have not felt for 10 days, is about to return. Not at 1 G, at 3 or 4 G. The bodies that their muscles and cardiovascular systems have been maintaining for 10 days, without gravitational load, are about to be asked to perform under conditions that would challenge even a fully adapted Earth-trained person. The first few seconds after the G-forces begin building are described by returning astronauts as a kind of physical shock. The return of weight is sudden and initially disorienting. The pressure of the seat against the body, the weight of the pressure suit on the shoulders, the feeling of the restraint harness pulling against the chest and hips. These sensations, which were absent for 10 days, return all at once and intensify as the G-forces build. Breathing becomes more effortful under high G loads. The diaphragm, which in normal gravity simply contracts and relaxes to pull air in and push it out, is working against the additional weight of the chest wall and abdominal organs during high G re-entry. The crew members, trained for this, breathe with a specific technique, forcing air in and out with more deliberate effort than normal breathing requires. The pressure suits help somewhat, providing some support to the chest wall. But the experience is one of sustained effort, not agony, but a continuous physical demand that is unlike anything experienced in normal gravity. The noise inside the capsule during re-entry is significant. The plasma roaring past the heat shield and the capsule body creates a sound that penetrates even the thick capsule walls. It is not a single tone, but a broad band roar, the acoustic energy of supersonic flow past a blunt body, with the specific resonances of the capsule's structure added to it. The crew members, trained through simulation to expect this sound, know what it means. But knowing intellectually what the sound represents, and being inside it for several minutes while strapped to a chair, under 4 times the force of gravity, are different experiences. The windows show a specific color sequence during re-entry. In the early phase, before the plasma fully forms, the view through the windows shows the dark blue-black of the thin upper atmosphere and the curvature of the Earth below. Then, as the plasma forms and thickens, the windows begin to glow. The plasma sheath is all around the capsule, above, below, on all sides, and the light from it comes through the windows as a shifting, pulsing orange and pink and white light. Inside the capsule, this light fills the interior with a reddish glow. It is beautiful in the way that a lightning strike is beautiful, striking and terrifying simultaneously. The radio blackout is perhaps the most psychologically isolating element. For 10 days, the crew has been in near constant contact with mission control. There have been scheduled sleep periods during which the communication was reduced, but the crew has never been more than a few minutes from a conversation with the flight controllers who are tracking every aspect of the mission. Now, in the most dangerous 15 minutes of the mission, that contact is severed. The crew is alone in the most immediate sense of the word. The radio is silent, and the voices of the people who have been watching over them are gone. The training for this moment is extensive. The crew knows the blackout is coming. They know its approximate duration. They have practiced re-entry many times in the full-fidelity simulation facility at Johnson Space Center, experiencing the procedures and the timeline until they are as deeply ingrained as any physical skill. But there is a specific quality to being truly physically isolated, not in a simulation where everyone knows it's a simulation, but in the actual capsule, in the actual atmosphere, with the actual stakes. That simulation can prepare you for intellectually, but cannot fully replicate emotionally. The crew of Artemis II will be as prepared as any humans have ever been for what they are about to experience. They will also be experiencing something that no living human being has experienced since the last Apollo astronaut re-entered from lunar distance in 1972. The institutional knowledge of what this feels like, the experiential knowledge transmitted from crew to crew through direct conversation and mentoring, has been absent for 52 years. The Artemis II crew will learn what it feels like from the simulator and from the written accounts of astronauts who have not done this thing in their lifetimes. They will learn what it really feels like in the 15 minutes, what the crew does during the blackout, during the most dangerous period of the mission, with no communication and nothing to do but wait, is a question that the training addresses through procedure, but that each crew member ultimately answers privately. The procedure during re-entry blackout is to monitor the capsule's instruments, to remain alert for off-nominal indications, and to be prepared to take manual action if the automatic systems fail. In practice, the monitoring is limited. The instruments can tell the crew the G-load, the capsule's attitude, the temperature readings from the heat shield sensors, and the navigation state. They cannot tell the crew whether the heat shield is cracking. The temperature sensors embedded in the heat shield structure at multiple depths through the avcoat and into the underlying honeycomb substrate are the most direct window the crew has into the heat shield's performance in real time. If the thermal protection is functioning nominally, the temperature at each sensor depth rises at approximately the predicted rate and remains within the predicted band. If the thermal protection is failing, if more heat is penetrating through the shield than expected, the deeper sensors will begin to read higher temperatures than predicted. The rate of rise will accelerate. The crew has been trained to recognize anomalous temperature readings and to understand their implications. In a scenario where the heat shield is failing, the sensor readings would tell them something is wrong. The question, one that no training can fully answer, because no one has been in this situation in real time, is what you do with the knowledge that your heat shield may be failing when there is nothing you can do to change the outcome. The capsule is in the atmosphere. The trajectory is committed. The physics is taking over. Knowing that the heat shield is failing is important for the post-flight record. It is not actionable. This is the specific quality of the most extreme risk in crewed spaceflight. Not the risk that comes with a clear decision point, where a choice can be made and the outcome follows from the choice, but the risk that arrives at the end of a committed trajectory, where the outcome is determined by whether the hardware performs, and the crew's role is to endure and monitor rather than to act. They will learn what it really feels like in the 15 minutes. Chapter 9. The Heat Shield Decision. What happens below them while they wait? There is a surface area of approximately 19.6 square meters on the base of the Orion crew module. Every square centimeter of that surface is covered with avcoat. Every square centimeter of that surface is, during the peak heating phase of re-entry, exposed to temperatures approaching 2,760 degrees Celsius, and the 4 people inside the capsule cannot see any of it, cannot check any of it, cannot verify in any way that is available to them in real time whether the material below their feet is performing as designed or whether it is doing something else. This is not a hypothetical problem. This is the actual situation. The crew of Artemis II will be making their re-entry with a heat shield that failed in an unexpected way on its first and only previous flight. The failure was not catastrophic, but it was real, and it was not in the models, and the full characterization of the failure mode took 2 years of investigation. The mitigations, the modified re-entry trajectory, the improved AVCOAT material, the updated computational models represent genuine progress in understanding the problem and reducing its severity. They do not represent certainty that the problem will not recur. What is actually happening below the crew during those 15 minutes at the surface of the heat shield is a sequence of physical events that the program has worked for 2 years to understand and model. Let's trace it in detail. In the seconds after entry interface, the temperature of the AVCOAT surface begins to rise. The aerothermal heating is initially gentle, but it builds quickly as the spacecraft descends into denser atmosphere. At the outer surface of the AVCOAT, the temperature reaches approximately 400 degrees Celsius. The onset of pyrolysis, the thermal decomposition of the organic matrix that gives AVCOAT its ablative properties. The outer few millimeters of AVCOAT begin to transform. The organic binders that hold the material together decompose into gases, which are driven outward through the matrix and into the boundary layer. The gases carry heat away from the material as they leave, a process called transpiration cooling, and they also react in the boundary layer with the incoming hot gas, partially blocking the heat from reaching the surface. Behind the pyrolysis front, the AVCOAT transforms into char, a highly porous carbonaceous structure with excellent thermal insulation properties. The char layer insulates the underlying fresh AVCOAT from the worst of the heating. The thermal conductivity of the char is very low, which means that heat flows through it slowly, and the temperature gradient through the char layer is steep, hot on the outside, cool on the inside. As the first dip reaches its peak heating phase, the char layer is perhaps a centimeter or 2 thick across the heat shield. The outer surface of the char is at over 1,000 degrees Celsius. The inner surface of the char, the boundary with the fresh AVCOAT below, is perhaps 300 to 400 degrees. The aluminium honeycomb substrate that forms the structural base of the heat shield is at perhaps 150 to 200 degrees. The primary structure of the capsule, behind the substrate, is at less than 100 degrees. The heat shield is working. The thermal gradient from 2,760 degrees at the stagnation point to less than 100 degrees at the structure. A drop of over 2,500 degrees across approximately 10 centimeters of heat shield is the physical accomplishment of the ablative thermal protection system. During the peak of the first dip, the char layer is also responding to the mechanical environment. The aerothermal forces on the heat shield are not purely thermal. There are also aerodynamic shear forces, the drag of the hypersonic flow across the heat shield surface that acts like a very high-speed, very hot wind. The char layer must withstand these shear forces while also being thermally stressed. It is, in physical terms, a material being simultaneously cooked, scoured, and mechanically loaded. The peak of the first dip passes, the spacecraft rises into the skip, the aerothermal heating drops. The char layer, which was in quasi-steady state during the peak heating, is now cooling. But it is cooling from the outside. The outer surface, which was at over 1,000 degrees and was in equilibrium with the incoming heat flux, is now losing that heat flux and beginning to radiate to the cold. Space above the skip trajectory. The interior of the char is still warm, having absorbed heat during the dip. The temperature gradient within the char is changing direction. During the dip, heat was flowing inward, from the outer surface toward the fresh avcoat. During the early skip, heat is flowing partly outward as the outer surface cools, and partly inward as the stored heat in the char conducts toward the cooler underlying avcoat. This reversal and redistribution of the heat flow within the char layer is the specific physical situation that the investigation identified as the driver of the anomalous char behavior on Artemis I, the thermal stress field within the char, the distribution of compressive and tensile stresses arising from the temperature gradients, changes character during this cooling phase, and in specific locations, the tensile stresses exceed the fracture strength of the char material. Char is not a ductile material. It does not deform plastically before it fractures. It is brittle. It fails suddenly, without warning, when the stress exceeds its strength. When a crack initiates in the char layer, it propagates quickly through the surrounding material until it reaches a region of lower stress, or until the crack tip encounters a structural feature that arrests it. The crack patterns observed on the Artemis I heat shield were consistent with this brittle fracture behavior. Relatively smooth fracture surfaces, crack orientations consistent with the stress field, crack lengths that were long compared to the microstructure of the char. The Artemis II heat shield avcoat has been manufactured with reduced void content, specifically to reduce the number of initiation sites for brittle fracture. In brittle materials, cracks almost always initiate at defects, voids, inclusions, surface irregularities, where the stress is locally amplified beyond the average stress in the material. Reduce the defects, and you raise the apparent strength of the material. The improved material should, in principle, have a higher resistance to the crack initiation that drove the Artemis I anomaly. Whether the improvement is sufficient, whether the remaining voids and defects in the improved material are small enough and sparse enough that the thermal stress of the skip phase will not initiate cracks, is the question that the arc jet tests have addressed, but not definitively answered. The sensitivity of this process to the specific manufacturing quality of the heat shield, the exact distribution of voids and inclusions in the avcoat that was applied to the Artemis II crew module, is part of what makes the flight test irreplaceable as a validation. Laboratory coupons test the average properties of the material. The actual heat shield is a specific physical object with a specific distribution of defects across its 19.6 square meters. And whether any particular region of the heat shield cracks during the skip phase depends on the specific defect density in that specific region encountering the specific thermal stress that the modified trajectory and the skip geometry produce at that location. The probability that the heat shield performs nominally is not the probability that the average material sample performs nominally. It is the probability that no region of the specific heat shield, with its specific defect distribution, encounters a combination of thermal stress and local material weakness that exceeds the fracture threshold. The ArcJet tests have tested samples from the improved material and found improved performance. They have not mapped the full heat shield and identified every potential initiation site for crack formation. This is not a failure of the program's approach. It is a fundamental limitation of pre-flight testing for complex components with spatially variable properties. The only way to fully characterize the heat shield's performance under the actual flight conditions is to fly it, which is exactly what the program is doing. Below the crew, in those 15 minutes, the AVCOAT is making this decision on a molecular level, one defect at a time, in an environment that no one in the program has ever fully characterized, and that will not be fully characterized until after the flight is complete. This is not a comfortable statement. It is an accurate one. Chapter 10. The physics they cannot control. 15 minutes is long enough to know that something has gone wrong, not long enough to fix it. This is the fundamental character of the re-entry problem, and it is different from almost every other failure scenario in crewed spaceflight. On the way to the moon, most failure scenarios allow for some response. An engine can be fired, a trajectory can be corrected, a backup system can be activated. The free return trajectory that Artemis II uses for the lunar flyby exists specifically to preserve the option of returning to Earth without a propulsive burn in the event of a propulsion failure. The mission architecture is built around the concept that failures should, wherever possible, have responses. Re-entry is the exception. Once the spacecraft has entered the atmosphere and committed to the re-entry trajectory, the number of meaningful responses available to the crew shrinks dramatically. They cannot abort out of re-entry. They cannot change the peak heating rate by flying differently. The trajectory is determined by the physical laws governing a blunt body moving through the atmosphere, and the crew's only control is the attitude of the capsule, which affects the direction of the aerodynamic lift that the skip maneuver depends on. They can, in principle, adjust the skip geometry by controlling the capsule's attitude, entering the skip phase with a slightly different angle of attack, for example. But these adjustments are small, and their effects on the heat shield thermal environment are limited. The physics of the re-entry is, in the most direct sense, not under human control. It is under the control of the atmosphere, the trajectory, the shape of the capsule, and the material properties of the heat shield. The crew's role during re-entry is to monitor the spacecraft's systems, to execute the nominal procedure, to intervene in the event of specific off-nominal conditions that the procedure defines responses for, and to endure the physical environment. They are not flying the spacecraft in the sense of making continuous, real-time control inputs that determine the outcome. The outcome is determined primarily by the physics, and the physics was set in motion at the moment the trajectory was committed to. This is not a failure of spacecraft design. It is a fundamental feature of the aerothermal environment of re-entry from lunar distance. The energies involved are so large, the timescales so compressed, the physical mechanisms so dependent on the material behavior of the heat shield, that the concept of real-time human intervention in the critical failure modes is not viable. What is viable is ensuring that the hardware works correctly before the mission flies, and monitoring the hardware during the mission to detect failures as early as possible. The monitoring has specific limitations that the crew and mission controllers understand. The heat shield temperature sensors provide information about the thermal state of the shield. They can detect anomalously high temperatures at depth, which would indicate that more heat is penetrating the shield than expected. But they cannot detect char cracking directly. They cannot measure the remaining thickness of the char layer. They cannot tell the crew whether the char is intact or fragmented. They can only report temperature, and temperatures that fall within a nominal range can still be consistent with a heat shield that is behaving anomalously in ways that have not yet produced a detectable temperature anomaly. The specific timing matters. The peak heating during the first atmospheric dip lasts approximately 3 to 4 minutes. The char cracking, if it occurs, likely happens during the skip phase, perhaps 2 to 4 minutes into the skip, as the thermal stress builds during the cooling. By the time anomalous temperatures might be detectable in the heat shield sensors, the situation may be irreversible. The cracking has already happened, the char has already ejected, and the second heating pulse is beginning. There is also the question of communication. During the blackout, the crew cannot alert mission control to anomalous readings. Mission controllers can receive some telemetry from the spacecraft through the plasma, but it is limited. Not the full data stream that the crew has access to in real time. If an anomaly is developing that would be visible in real-time data, the crew knows before mission control. If the crew identifies anomalous heat shield behavior during the skip phase, they know in the radio blackout that the situation may be deteriorating, and they cannot tell anyone. The documentation and communication of what the crew experiences during re-entry, specifically any anomalous observations from the heat shield sensors, is one of the reasons that verbal reports immediately after the re-entry blackout ends are important. The moment the radio blackout lifts, the crew will be asked for a status report, and one of the most important elements of that report is the heat shield thermal data from the re-entry phase. If the data shows anomalies, the program needs to know immediately. Not for this re-entry, which will be over by then, but for every subsequent mission that uses the same spacecraft configuration. Chapter 11. What mission control is doing in those 15 minutes. The Mission Control Center at Johnson Space Center in Houston has been operating continuously for the duration of the Artemis II mission. The flight controllers, the people who occupy the consoles in the mission control room during the flight, are organized into teams, each responsible for a specific set of spacecraft systems. The flight director is the senior controller, responsible for all decisions during the flight. The flight dynamics officer is responsible for the trajectory. The environmental control and life support systems controller is responsible for the cabin atmosphere. The propulsion systems controller is responsible for the engines and thrusters, and so on, through every system on the spacecraft. For most of the 10-day mission, the mission control room has been a place of focused but not acutely intense activity. The major maneuvers, the translunar injection burn, the lunar approach maneuvers, the return trajectory burns, have been executed and completed. The systems have been working. The crew has been healthy. The rhythm of the mission has settled into the routine of a 10-day deep space flight. During the 15 minutes of re-entry, the mission control room is a different environment. The flight director has been in the chair since several hours before entry interface, leading the detailed review of the entry checklist, confirming that every system is in its correct configuration for entry, verifying that the recovery forces in the Pacific Ocean are in position, receiving updated atmospheric condition reports for the landing zone. The recovery ship, the USS San Diego for Artemis II, has been pre-positioned in the expected splashdown zone, and the recovery swimmers and medical team have been briefed and are ready. When the service module is jettisoned and the crew module is alone, the mission control team transitions to a heightened state of focus. The trajectory is being monitored in real time by the flight dynamics officer, who is tracking the spacecraft's position and velocity against the predicted trajectory, ready to report immediately if the entry angle deviates from the planned range. The entry angle is critical, too steep, and the deceleration is too severe, potentially causing structural failure and certainly causing G-loads beyond human tolerance. Too shallow, and the spacecraft skips off the atmosphere entirely and returns to space on a trajectory that may not lead back to Earth safely. The nominal entry corridor for Orion is relatively narrow, approximately half a degree of flight path angle. Half a degree at these velocities represents a meaningful difference in the entry environment. The navigation system aboard Orion, which combines inertial navigation with star tracker data, is accurate enough to target the entry corridor with high reliability. And the trajectory has been computed and verified multiple times in the hours before entry interface. But the specific trajectory flown depends on the navigation system's accuracy and on the spacecraft's attitude control during the final approach to entry interface, both of which introduce small but non-zero uncertainties. The spacecraft passes through entry interface and begins to heat up. The temperature data from the heat shield sensors begins arriving in mission control through the limited telemetry that gets through the plasma. It is not the full data stream. The plasma attenuates the telemetry, and what arrives is partial and intermittent. But what does arrive gives the mission control team a real-time window into the heat shield's thermal state, and the flight director is watching it in parallel with the trajectory data. The radio blackout begins. The voice communication ceases. The mission control room goes quiet in a specific way. Not silent, because there is still constant activity at the consoles, but without the continuous voice loop that has connected the crew and mission control for 10 days. The flight controllers continue monitoring their specific systems from the intermittent telemetry that comes through the plasma. The room is focused, still, waiting. The flight dynamics officer is tracking the spacecraft's trajectory from the radar data. The radar can see the spacecraft through the plasma. Radar waves are not absorbed by the plasma the way radio communications are. The trajectory is nominal. The spacecraft is on the planned path. This is the most important information available during the blackout. The heat shield thermal data, arriving intermittently through the plasma, is being watched by the spacecraft system's controllers. In a nominal re-entry, the temperatures rise at predicted rates, peak at predicted values, and then begin to fall as the aerothermal heating subsides during the skip. If the temperatures are rising faster than predicted, or if the deeper sensors are showing anomalous readings, the controllers will flag it immediately. There is nothing they can do to change what is happening to the heat shield. But knowing that there is an anomaly affects how the post-blackout communications are prioritized. Then, after the final re-entry plunge, and as the spacecraft decelerates into the subsonic regime, the plasma thins. The radio signal begins to come through, static at first, and then a voice. The crew's first words after the blackout, typically a brief status report confirming that the spacecraft is performing nominally and the crew is in good condition, are among the most significant communications of the entire mission. Every person in the mission control room has been holding their breath, in a metaphorical sense, for the duration of the blackout. The mission has been in progress for 10 days. Every system has been watched and managed and cared for by the teams at the consoles, and now, in the 15 minutes of re-entry, control has been surrendered to the physics. The flight controllers know their spacecraft. They know its systems. They have been living with this mission for years in training and for 10 days in flight. And in these 15 minutes, the outcome is not in their hands. The moment the radio blackout clears and the crew confirms they are alive, and the spacecraft is intact, is the culmination of a specific kind of sustained, professional vigilance that has no real parallel in most human occupations. Flight controllers at Mission Control are selected and trained specifically for their ability to maintain focused performance over extended periods, to absorb and process large amounts of technical data simultaneously, to make rapid decisions under uncertainty, and to maintain calm under pressure. The selection process is rigorous and the training is extensive. A flight controller does not sit at a console for a real mission until they have demonstrated competency through years of simulation and qualification. The people in the mission control room on the day of Artemis II's re-entry will be among the most carefully prepared professionals in any field. They will also be experiencing something that is unique to mission-critical spaceflight operations: the sustained responsibility of watching over the lives of people who are in a situation where nothing the controllers do can change the immediate outcome. During nominal cruise operations, a flight controller's actions directly affect the mission. A decision to fire a thruster changes the trajectory. A decision to switch a power system changes the electrical state of the spacecraft. During the 15 minutes of re-entry, the flight controller's role shifts from active management to attentive witnessing. They cannot improve the heat shield's performance. They cannot adjust the trajectory. They can only watch the telemetry and wait. This specific kind of helpfulness, doing the right things over months and years of preparation so that the critical 15 minutes go well, and then having no active role in those 15 minutes themselves, is one of the defining characteristics of the people who run human spaceflight missions. The value they provide is in the preparation, not the execution. The execution, in those 15 minutes, belongs to the physics and to the hardware. The first voice contact after the blackout, the moment when the static on the communications loop suddenly resolves into a voice saying, "Houston, Orion, we're showing nominal systems," is a moment that flight controllers who have experienced it describe as physically releasing a tension they had not been fully aware they were carrying. The 10 days of mission, the months of preparation, the years of training, all of it is present in that moment, in a room full of people who know exactly what they were waiting to hear and are hearing it. The moment the radio blackout clears and the crew confirms they are alive and the spacecraft is intact, is the moment 10 days of continuous monitoring crystallizes into a single overwhelming fact. It worked. For a few seconds after that first communication, the mission control room allows itself to feel what it has been carrying for the duration of the flight. The quiet intensity of people doing difficult and important work under the weight of knowing exactly what is at stake. Then the recovery begins. Chapter 12. The 3 scenarios. What success, partial failure, and catastrophic failure actually look like. It helps to be specific about what each possible outcome of the 15 minutes actually looks like, because the range of outcomes is not binary, not simply fine or catastrophic. There's a spectrum of outcomes, some more probable than others, and understanding where on that spectrum the current program's risk management leaves things is the honest assessment of the situation. The first scenario is nominal success. The trajectory is correct. The first dip heats the heat shield as predicted by the updated models. The improved AV-coat material, with its reduced void content and improved uniformity, forms a more robust char layer than Artemis I. During the skip phase, the char layer cools with less thermal stress than was sufficient to cause the cracking and ejection observed on Artemis I. The second heating pulse encounters a substantially intact char layer that provides the predicted thermal protection. The deceleration proceeds nominally. The blackout lifts. The drogue parachutes deploy at the correct altitude. The main parachutes deploy at the correct altitude. The capsule descends at 28 kilometers per hour. It hits the Pacific Ocean surface. The seat absorbers absorb the impact. The crew is bruised and disoriented, but alive. The recovery swimmers arrive. The hatch opens. 4 people who flew to the moon come out into the salt air of the Pacific with the sky above them, and the mission is over, and everyone is going home. This is the most probable scenario. The engineering work that has been done, the mitigations that have been implemented, the testing that has been conducted, all of it points toward this outcome as the most likely one. The probability of nominal success is high. Not certain, but high. The second scenario is anomalous but survivable. The trajectory is correct. The heat shield performs adequately, but not nominally. The improved AV-coat material does not fully prevent the char cracking and ejection that occurred on Artemis I. The char ejection during the skip phase is somewhat more severe than on Artemis I, but the updated trajectory modification and the improved material together limit the cascade. The second heating pulse encounters a heat shield with more anomalous material loss than ideal, but the thermal protection is maintained throughout reentry. The crew survives. The post-flight inspection finds more extensive anomalous char behavior than the pre-flight models predicted. The program faces a second round of investigation before Artemis III can proceed. This is the scenario that most concerns the engineers who worked through the Artemis I anomaly. Not because it kills anyone, it doesn't, but because it means the problem is not yet understood and not yet solved, and the next mission, Artemis III, returning from a crewed lunar landing at higher velocity, will face a more demanding thermal environment with a heat shield whose behavior the program still cannot fully predict. The third scenario is partial heat shield failure. The char ejection during the skip phase is substantially more severe than on Artemis I. The cascade scenario, char ejection exposing fresh avcoat, rapid recharring, further cracking, proceeds to a degree that depletes the heat shield thickness beyond the nominal margin in one or more regions of the heat shield. During the second heating pulse, the heat penetrates to the honeycomb substrate in the depleted region. The substrate heats to beyond its structural limit. The local thermal protection fails. In this scenario, the spacecraft does not immediately disintegrate. The failure is local, not global. The heat shield is depleted in a region, and thermal damage begins to propagate through the capsule structure in that region. Depending on how large the depleted region is and how far the thermal damage propagates, the outcome could range from structural damage that the spacecraft survives, with significant damage that would be catastrophic for any subsequent mission, but that allows this re-entry to complete, to structural failure of the capsule during re-entry. The survivability of a partial heat shield failure scenario depends on a number of factors that are not fully deterministic. The size and location of the depleted region, the rate at which thermal damage propagates through the capsule structure, whether the parachute deployment mechanisms are affected by the thermal damage, and whether the capsule maintains aerodynamic stability throughout the descent. This scenario has a range of sub-outcomes, and the program's risk assessment attempts to characterize which sub-outcomes are possible and with what probability. The fourth scenario, which is the one that everyone is trying to prevent, is catastrophic heat shield failure. Before describing it, it is worth asking what the evidence from Artemis I tells us about how far the Artemis I heat shield was from this fourth scenario. This is not a question that has been publicly answered with a specific number, but the engineering analysis provides some guidance. The char ejection on Artemis I reduced the heat shield's remaining thickness in the affected regions. The question is, by how much and how that reduced thickness compared to the minimum thickness needed to provide adequate thermal protection through the rest of the re-entry. The program's assessment, which is what within acceptable limits technically means, is that the remaining thickness in even the most affected regions of the Artemis I heat shield was above the minimum required. The thermal protection was maintained. The margin was reduced but not exhausted. But margin reduction is not a linear predictor of risk. A heat shield that has used 90% of its margin in one flight is not 9 times more risky than one that has used 10%. The relationship between margin reduction and catastrophic failure risk is non-linear, and the specific non-linearity depends on the failure mechanism. If the failure mechanism is the cascade, char ejection leading to rapid recharring leading to more ejection, then the margin can go from substantial to exhausted quickly once the cascade initiates, because each cycle of the cascade removes material at a rate higher than the nominal ablation rate. The fact that Artemis I survived does not tell you, without additional analysis, exactly how much additional severity would have been needed to cross the line from survived with reduced margin to did not survive. This is part of what the engineering investigation has been trying to characterize. Not just the failure mechanism, but the margin against catastrophic failure under different conditions. The updated models and the arc jet tests are attempting to answer the question, at what severity of char ejection does the heat shield fail? Because knowing the answer to that question is necessary for knowing whether the improved material and modified trajectory provide an adequate safety margin. The fourth scenario, which is the one that everyone is trying to prevent, is catastrophic heat shield failure. The char ejection and cascade are severe enough that the heat shield is breached in a region large enough to allow the plasma to reach the primary structure. The aluminium primary structure burns. The structural integrity of the capsule fails during re-entry. The capsule does not survive. The crew does not survive. The probability of this fourth scenario, under the current program configuration, with the mitigations implemented, is low. It is not zero. The program's engineers believe they have understood the failure mechanism well enough and implemented sufficient mitigations to make this scenario very unlikely. The independent oversight community has expressed cautious confidence in the program's approach, while noting that the residual uncertainty has not been fully eliminated. The crew of Artemis II has reviewed the risk assessment. They have concluded that the probability of catastrophic failure is within the range of risk that they are willing to accept for a mission of this importance. They are correct that the risk level is not unprecedented. The early Apollo missions flew with risk levels that, by modern standards, would not be accepted without significant hand-wringing. What makes the Artemis II situation specific is not the absolute level of risk, but the fact that the risk is partially characterized by physics that was discovered in flight rather than in testing, and that the mitigations have been validated by testing that approximates but does not replicate the flight environment. The residual uncertainty, the gap between what the program knows and what it would need to know to be fully confident, is real. It is being carried into the flight. Chapter 13: The Moment That Matters. Why? These 15 minutes define the program. The 15 minutes of re-entry are not just the most dangerous period of the Artemis II mission. They are, in a specific and consequential sense, the most important 15 minutes in the American human spaceflight program since the Columbia disaster in 2003. After Columbia, NASA spent 2.5 years grounded, investigating, redesigning, and re-qualifying the space shuttle for flight. The investigation revealed not just the specific physical cause of the accident, foam strike damage to the wing leading edge, but the deeper institutional causes, the organizational dynamics that allowed a known safety concern to be treated as an acceptable risk, the communication failures that prevented the full extent of the concern from reaching decision makers, the normalization of deviance that made a dangerous condition appear normal. The reforms that followed were real and substantial. The foam strike problem was addressed. The communication structures within the program were changed. The safety culture was explicitly reinforced. The return to flight process was extensive and rigorous, and when Discovery flew in July 2005 on the first return to flight mission, it returned successfully. The Artemis II program has a similar structure, not identical, but analogous. A technical anomaly was discovered in the heat shield after the first test flight. The anomaly was not in the models. Investigation was conducted. Mitigations were implemented. The program is now preparing to fly with crew. The question of whether the investigation was thorough enough, the mitigations adequate, and the residual risk within acceptable bounds is exactly the question that the program's engineers and the independent oversight community have been working on for 2 years. If Artemis II succeeds, if the 15 minutes complete nominally, the crew survives, and the heat shield performs within the predicted range, the program will have demonstrated something that has been in question since December 2022. That it understands the heat shield failure mechanism, that its mitigations are effective, and that Orion can safely carry a crew through the most demanding phase of a lunar return mission. This demonstration is not just important for Artemis II itself. It is the necessary precondition for every subsequent Artemis mission, for the crewed lunar landing of Artemis III, for the sustained lunar program that the Artemis architecture envisions. A successful re-entry on Artemis II clears the path. Not just technically, but institutionally. It resolves the largest open question about the program's ability to execute, and it provides the foundation of validated performance data that the program needs to plan subsequent missions with confidence. If Artemis II does not succeed, if the 15 minutes produce an anomalous or catastrophic outcome, the consequences are not limited to the loss of the crew, however devastating that loss would be. The consequences for the program, for the space agency, for the American strategic position in the space race with China, for the commercial space ecosystem that has been building around the Artemis architecture. All of these are severely affected by a program failure at this stage. A crewed spacecraft failure during re-entry in the post-Columbia era would be the most consequential setback in American crewed spaceflight since Columbia. Possibly more consequential because the Artemis program is operating in a strategic environment, the competition with China for cislunar dominance, that adds urgency to the recovery timeline in a way that the post-Columbia situation did not. But the alternative to flying, indefinitely delaying the crewed mission while the program seeks a level of certainty that the physics may not allow, has its own costs. Every year of delay is a year during which the Chinese program is advancing, a year during which the program's budget is being consumed without a crewed flight to show for it, a year during which the coalition of international partners assembled around the Artemis Accords is subjected to questions about whether the American program can actually deliver. The 15 minutes of Artemis II's re-entry are the resolution point for all of this tension. They are the moment when the program's engineering judgment, its assessment of whether the mitigations are adequate, whether the residual risk is acceptable, whether the spacecraft is ready to carry crew, meets the physical reality of the flight environment. 4 people will be in the capsule. The heat shield will be doing what it does. And here, at the end of everything, is the thing that matters most about how we talk about this. The crew of Artemis II did not accept these risks blindly. They accepted them with the full weight of informed professional judgment applied to every detail of the engineering case. Reed Wiseman has been in the room for every heat shield review. Victor Glover has been involved in the technical deliberations as both a crew member and an active participant in the program's engineering culture. Christina Koch and Jeremy Hansen have the same access to the full technical picture that every astronaut assigned to a mission has, complete, detailed, and updated as the investigation has progressed. When those 4 people made their decision to fly, they were not making it in the abstract. They were making it knowing what the Artemis I heat shield looked like after recovery, knowing what the arc jet tests showed, knowing what the updated models predict, knowing where the uncertainty lies, knowing the history of the Challenger and Columbia investigations, and what institutional failures contributed to those losses. They made the decision that this program has done the work, that the mitigations are real and substantive, and that the residual risk is within the range that the mission's importance justifies accepting. That judgment deserves to be right. 4 people will be in the capsule. The heat shield will be doing what it does. The physics will take over. And in approximately 15 minutes, the question that has been the central uncertainty of the American lunar program since December 2022. Can the spacecraft safely return a crew from the moon? Will have an answer. Conclusion. 15 minutes between everything and nothing. Here is what those 15 minutes are, stripped of every abstraction. They are 11 kilometers per second, becoming 8 meters per second. They are the kinetic energy of a return from the moon being converted by the atmosphere into heat and then into slowness. They are the plasma hotter than the surface of the sun, and the avcoat burning away in controlled, progressive ablation to absorb it, and the char layer doing what it was designed to do. Or perhaps doing something else, something it was not supposed to do, something that an uncrewed mission already revealed it was capable of. They are 4 specific people in specific pressure suits, in specific seats, strapped into a specific capsule that has flown exactly once before. 4 people who have spent years of their lives preparing for this mission, who have gone farther from Earth than any human being in 52 years, who have seen the moon from 8,900 kilometers and the Earth as a marble from 370,000 kilometers, who have spent 10 days in a machine the size of a large minivan, and who are now, in these 15 minutes, being returned to their planet by the same physics that threatens to kill them. They are the silence of the radio blackout, the mission control room holding the weight of 10 days of continuous watchfulness, while the radar track is the only confirmation that the capsule is still there. They are the heat shield sensor readings, climbing at predicted rates or not, the temperature at each depth through the avcoat, either confirming that the physics is proceeding as modeled or whispering something else, something the engineers have been trying to hear for 2 years. They are the drogue chutes deploying, those 2 sudden jerks as the fabric catches the air, and then the main chutes, 3 of them, each 35 meters across, opening in sequence, each jerk a confirmation that the system that was packed and sealed before launch and carried through the vacuum of space and the aerothermal violence of re-entry is doing what it is supposed to do. They are the capsule swinging under the parachutes, descending toward a specific patch of the Pacific Ocean where the USS San Diego is waiting, where the recovery swimmers are ready, where the media satellite feeds are live, and the mission control room is full and the families are watching. And then they are splashed down. The impact of 9,300 kilograms on the surface of the Pacific Ocean at 28 kilometers per hour. The brief, violent spike of the water impact absorbed by the seat systems. The capsule settling and righting itself in the water. The flotation devices deploying, the hatch opening, and 4 people who have been to the moon coming out into the salt air. Those 15 minutes are the culmination of everything that the Artemis program has built. They are the answer to the question that Artemis I raised in December 2022, when the heat shield showed the world something it was not supposed to show. They are the demonstration, or the failure of the demonstration, that the United States can do this again, send human beings beyond Earth orbit and bring them back safely. The mathematics of the 15 minutes is simple. 11 kilometers per second minus 10.997 kilometers per second equals 8 meters per second. All the rest, the plasma, the char, the skip, the parachutes, the recovery, is the mechanism by which that subtraction is accomplished. The mechanism works at its best with a precision and elegance that represents one of the finest achievements of engineering that human beings have produced. At its worst, it fails. And failure in those 15 minutes, at those velocities, against that thermal environment, leaves nothing to recover and nothing to investigate until the parachutes don't appear on the radar and the recovery ship has nothing to find. The 4 people who will be inside those 15 minutes know both of these things. They have chosen to go. The program has worked to make the first outcome more likely and the second less likely. The investigation is complete, the mitigations are in place, the trajectory has been modified, the material has been improved, and the engineers have done everything they know how to do with the physics and the data they have. In 15 minutes, the flight will either end in the Pacific Ocean with the crew, alive, or the question of whether the heat shield held will stop being a technical question and become a memorial. The choice to go, made by 4 people who understood exactly what they were choosing, deserves to be met by everything the program has to give, not just the engineering, but the honesty about what remains unknown, the willingness to hold a line against the pressure that has preceded every major human spaceflight accident, and the respect for what those 15 minutes actually are. They are not a milestone. They are not a demonstration. They are the moment when 4 human lives depend on whether the Avcoat holds. We should hope it does. We should ensure that every decision made to get there gave it the best possible chance. And we should remember what those 15 minutes represent beyond the immediate mission. The last time human beings re-entered Earth's atmosphere from beyond Earth orbit was December 17th, 1972. The crew of Apollo 17, Gene Cernan, Harrison, Schmidt, and Ronald Evans, splashed down in the Pacific Ocean after the final Apollo lunar mission. Their re-entry at similar velocities and similar G-loads similarly depended on the aerothermal physics of ablative heat shield protection. They came home safely, and then, for 52 years, no one returned from beyond Earth orbit because no one went beyond Earth orbit, and the particular knowledge of what a lunar return re-entry actually feels like, not in a simulator, but in the actual capsule at the actual velocity, became history rather than experience. The crew of Artemis II will restore that experience. In those 15 minutes, they will do something that no living human being has done. Not an approximation, not a simulation, not a recreation, but the actual physical act of returning from the moon, protected by an ablating heat shield, at 11 kilometers per second, through a plasma hotter than the surface of the sun, with the Pacific Ocean waiting below. Knowledge they bring back from those 15 minutes. The sensor data, the visual observations, the physiological data, the crew's own accounts of what they felt and heard and experienced, is irreplaceable. It is the kind of knowledge that can only be generated by actually doing the thing, and it is the knowledge that will make every subsequent Artemis mission safer, more precisely planned, and more confidently executed. If those 15 minutes go well, they represent not just the survival of 4 specific people, but the resumption of a capability that humanity allowed to lapse for 52 years. The capability to return from the moon, the capability to go beyond the boundary that has confined human spaceflight since 1972 and come back safely to Earth. Those 15 minutes are worth getting right. We should hope it does. We should ensure that every decision made to get there gave it the best possible chance.